to the HMAC key, and then apply the HMAC. And that truncated to the first 128 bits gives you the IV for this chunk. Now, the keys are randomly generated when you create your file vault, and then they are wrapped in the header of an image. Now, this header is, well, it's kind of a misnomer because sometimes it's a header that's in the old versions, like there's version 1 and version 2 of the metadata format. And in version 1, it was actually at the beginning of the disk image, and in version 2, it's at, sorry, the other way around. In version 1 of the format, it was at the end of the disk image. In version 2, it's at the beginning of the disk image. Now, what's interesting is that the wrapping of these AES keys is done using triple DES for some reason. So, in fact, I mean, it's kind of cheating because now the security doesn't only depend on AES, but if either AES or triple DES folds, you're screwed, right? Okay, and what they did when they went to version 2 of the metadata format, which was, I think, in Panther, is they introduced an option for having an additional asymmetrically encoded header. And what this is good for is for a recovery feature. I'll go into that a little later. First, let's look at the normal way you unlock your file image again. So the passphrase for your file image is your normal login password. So if your login password is wrong, is weak, your file is useless as well. What they use for deriving the key for unwrapping the other keys is something called PBKDF2. That's a very standard algorithm. It's in the RSA PK CS5 series of algorithms. And they use this algorithm, which is parameterized with 1,000 iterations, which is, well, it's kind of low. But you don't want to wait forever for your disk image to attach, so that's probably why they choose a low number of iterations. And what's interesting as well is that most of the crypto parts are actually implemented in something called CDSA. That's the common. Sorry, it's an architecture for cryptography that was developed by Intel, and this architecture actually is open source, and it's modular as well. So it's like bloat. I mean, there's this huge meta framework, and then you have providers sitting in this meta framework, and there's one Apple CSP provider. And this is also what makes like porting like the reverse engineered implementation kind of hard, because then you have to port all of the other crap as well. I mean, CDSA exists on Linux as well, but you'd have to port the Apple CDSA provider. So what we decided to do for the free implementation was we did away with all of the CDSA stuff, and we used OpenSSL instead, because that's much leaner. For performance reasons, Disk Images has its own AES implementation. However, it pulls in the SHA-1 from an OpenSSL lib. So this is kind of inconsequential as well, because I mean they have CDSA, but some stuff comes from other parts. And the wrapping that they've introduced in version 1 of their header format, which they've discarded again in version 2, is loosely based around a standard that is commonly referred to as PKCS7, which is RFC 2630. And what is kind of funny about this is they wanted to implement it with a random IV that they store on the drive, and they actually do store this IV on the drive, but they don't actually use it. So it looks like somebody, started an implementation and, got held up and didn't quite finish, and then they ditched it and went to another header format. But all that stuff is open source. The reverse engineering was just the disk images framework. Okay, now to the recovery mechanism. When you enable File Vault, you can, or basically you have to set a master password. This master password, in turn, protects a keychain that is in your library keychains directory. And this recovery keychain, it's called, contains one certificate and one private key. And this private key is a 1024-bit RSA key. By having this key, you can decrypt another struct in the metadata that also contains the blob where the encryption password and the HMAC password for decrypting the real data that's in your File Vault images is contained. Now, the problem is there's something called the Lenstra-Verheul heuristic. And what this does is basically it establishes a mapping between the parameter sizes of symmetric and asymmetric key cryptography. And, well, Apple claims they have 128-bit security, but this, if you have set a master password, is not quite true. Because by having set a master password, you have this 1024-bit key on your drive, which is, this key is not encrypted, right? I mean, it's sitting out in the plain text. I should add, like, File Vault is only protecting your home folder. It's not protecting all of the other folders on your file system. Now, 1024 bits asymmetrically, according to Lenstra-Verheul heuristic, means 72 bits symmetrically. That's not a lot. Usually, these days, you should have at least 80. Okay, so that we went into already. The headers of version 1 live at the beginning of the file, and the version 2 headers live at the end. And in 10.4.7, they actually made the version 2 headers mandatory for sparse encrypted disk images. That's probably because when you log out, the disk images get compacted. Now, if you think about what happens if you compact a disk image, it shrinks, right? And you have the metadata at the end, and you have a power failure, for instance. Where's your metadata after that? Well, whoops, gone. So that's why you should have it like in the new format. Now, let's look at the gory details. The password header, in principle, is very, very generic. I mean, they could easily swap out the key derivation algorithm. They could swap out the PRNG algorithm that they use for generating temporal keys when you re-encrypt, for instance. They could have different algorithms for the symmetric encryption of the blocks. They could have different modes. They could have different paddings. But they don't actually use that. They just have one C-encrypted encoding. And that is, I mean, that statically is AES-128. That's kind of interesting, I think. I'm not sure what future versions of OS X have planned. But what I'd really like to see is Apple opening up the disk images framework and allowing other people to write plugins for it, because then you could theoretically also mount disk images, or rather loopback devices in the form of disk images from other operating systems, so you could have actual interoperability, something that's kind of missing in the market of disk encryption these days. I mean, there's TrueCrypt, which is cross-platform, but it doesn't run on OS X. And then there's PGP Disk, which runs on basically everything, including OS X, but it's not open source, really. So go to the next slide, please. Reversing the disk images framework was actually quite easy, because disk images is C++ code. And when you look at the binaries, you can extract like the full signatures of every method of a class if it's not obfuscated, and Apple has not obfuscated disk images. So all of the analysis basically was done using like OTool, GDB, and the debug output of HDIutil. HDIutil, I should add, has a little debug switch, which is great because when you turn it on, it gives you all of the internal, it gives you all of the internal steps it has done. It outputs you the HMAC SHA-1 key, it outputs you the encryption key, so you can verify that you've actually done the right thing when you've reverse engineered and have written your own implementation. Initially, I thought it might have been easier to reverse engineer disk image framework using something called Boomerang, which is a great reverse compiler, but unfortunately, although it supports Macho, the Macho binary format, which is the default on OS X, it doesn't really work so well with PowerPC code, and after I patched it to work with Intel code, it worked better, but it like bombed out on me in like 3/4 of the cases, so it wasn't really useful for generating more than like 1 or 2 functions from the binary. So, but actually, if you look at the disassembly, if you look at the PowerPC disassembly, it's not that hard to see what's going on because the calls that they make to the CDSA framework are very similar in structure. So once you've figured out one of the calls, you get the hang for the rest of them. You just have to be careful when because you have to follow a lot of pointers to the structures, and on OS X right now there are, as I'm aware of, no good reverse engineering tools. There's IDA Pro for Windows, but you cannot really use something. There's no similar thing such as IDA Pro on the OS X platform. Now, the results that we have is we have something called while fault decrypt. Actually, that's a spelling mistake on the slide. It should be a V and an F instead of an F and a V. What it does, you feed it an encrypted d-image, either like a sparse d-image or a non-sparse, like UDIF d-image, and it outputs you the decrypted d-image if you have the correct passphrase. This tool works with both version 1 and version 2 encrypted disk images, so even if you have like an old installation and you want to like transfer your data off that, but you don't have the install media, but another box which runs an open system, you can still get the data off it if you have the passphrase or if you can guess it. What it doesn't do is it doesn't expand the sparse images to a real disk image. This is kind of a problem still because what that means is if you have a sparse disk image, you can't mount that, say, on the Linux, because although Linux has support for HFS and HFS Plus, well, it doesn't know how to use sparse images. So what's needed here is like another converter that converts these sparse images to full-blown images that can be mounted. But that is fairly trivial from what I've seen. The code is very rough at the moment. For instance, it doesn't do the recovery thing yet, but we're working on that still. The code works, and it will only get better. What we also showed is that the cryptography of FileVault does not only depend on AS128, I'll reiterate that again to make the point, but it also depends on triple DES, which effectively has only a bit, an effective key length of 112 bits, and on the security of RSA-124. So if either of these 3 folds, you're screwed. The other thing that's bugging us about FileVault is that we'd actually like to have full disk encryption, not just the home directory, because there are a lot of applications that